Welcome to today's Elastic Virtual Meetup. I'm Faith Westorp from Elastic's community team. Today we're lucky enough to have Scott Herman from BlackSky. He's their CTO, and today he's going to be presenting to us on their use case. So really excited to have him. We're super lucky to have him here today. Really excited for this presentation. If you guys have any questions or comments throughout, you can use Zoom's Q&A feature or the chat. I'll be monitoring both so that we can address those as they come up. So without further ado, Scott, I'll hand things off to you.
Thanks, Faith. Hi, everybody. My name is Scott Herman, and I'm the CTO at BlackSky. We're a global monitoring company, and Elastic is a key part of the infrastructure that we use to analyze and produce intelligence products from the imagery that we take and from data that we get from other areas. What I'm going to do today is walk you through a briefing that talks a little bit about what we do at BlackSky, and then I'll interject some details along the way about how Elastic plays a part. We use Elastic for a lot of things. It's one of our core database entities, but we also use it for logging, monitoring, and a few other functions that I'll talk about more towards the end of the brief. Before I get started, Faith, can you hear me okay?
Yep, I can hear you great.
Okay. So, and can you see my PowerPoint now?
Yep, we can see your PowerPoint.
Okay, fantastic. Well, let's get going then. So as I mentioned, BlackSky is a global monitoring company. And we monitor the globe through what's called remote sensing. And remote sensing can be satellites, it can be aerial sensors, it can be environmental sensors or ground sensors, anything where you're basically standing off from the thing that you're monitoring. You're not directly instrumenting it, you're viewing it from afar and trying to assess what's going on. So for example, we were monitoring last year the Turkish incursion into Syria along the border. And so we were taking pictures of border crossing points to try to assess when the Turks were going to start their incursion, and what avenues of approach would they take, what kind of damage were they doing along the way, and what was the response going to be. So unlike the satellite pictures that you're probably familiar with through things like Google Maps or Apple Maps, these are images that are turned around very, very quickly. We task the satellite, we take the shot, we get it back, we analyze what's happening in the shot, and then we try to make a determination as to what's going on. The way our customers use this is they'll get notifications of activity, of anomalies that are happening in those areas. Here's an example of a couple email alerts that I got on my cell phone that were basically telling me that, look, we've got new imagery available as the Turks move across the border into Syria. A different example, this is the Saudi Aramco plant in Saudi Arabia that was attacked last year. And this is imagery that was taken just a few hours after the attack that allows us to do some assessments of where was the damage, how extensive is the damage, and what does the recovery look like? How fast is reconstruction starting? From that, we may be able to make some predictions in terms of how long is this facility going to be down? What are the potential impacts on things like the oil commodity supply chain and oil pricing? The way we do this is we use a primary source, which is a small satellite that basically takes pictures of the Earth from space. We are in the process of building a swarm of satellites that will circle the Earth, taking pictures all throughout the day and delivering those pictures back to our customers along with analysis of what's happening. So here's an example of one of our first satellites. It's actually sitting on the pad, and up it goes. So this is pretty exciting. We are launching these satellites several times a year on a variety of launchers. We launch out of India, we launch out of California, we launch at several different locations around the world. And this is an example of kind of the imagery that comes back. This particular shot is of a airbase in the southern part of the Emirates in the Arabian Gulf or the Persian Gulf. And it kind of gives you a sense of what kind of detail you can make out when you take these pictures from space. Here's another example. This is Barcelona Harbor in Spain. And several things jump out of this image. And again, remember, this image was taken with a small satellite. So fairly cost effective, allows us to put many different satellites up and bring that information back. And several things you can see in this image. You can see the container port. So we're looking at things like, what is the churn of the containers? How much volume is going through? How busy is that port? Has it been impacted by the COVID crisis in terms of throughput and performance? What ships are docked there? Are we seeing a normal flow of traffic, or are we seeing things frozen up because of the pandemic? You can see things like sports stadiums and residential areas and oil storage tanks. All of these are things that we can measure. You can see a train yard. So we can measure the number of cars in the train yard and how often are trains and freight going in and out of that facility. So there's a lot of things you can get from a picture, not just what it looks like, but most of the things you can see on the screen are things that you can measure over time. And if you take frequent enough pictures, you can start establishing what's called a pattern of life. And that's basically saying, what are the trends? What is normal for this facility? And how do you determine when something has gone abnormal? And the one we're all dealing with right now, of course, is the global economic shutdown related to the pandemic. So a lot of things to watch and monitor right now. Now, what gets interesting about what we're doing and how we're different from the kind of satellite imagery that has existed in the past, again, the kind of imagery you may be used to in Apple Maps or Google Maps, which may be years old. This is basically 4 shots of Barcelona all taken on the same day from 4 different satellites. So you'll see there Global 1, Global 2, Global 3, Global 4. Those are the names of our first 4 satellites. So these are pictures taken throughout the day, early morning, midday, late afternoon, all watching that port in Barcelona. We also monitor a lot of other activities. It's not just about satellite imagery. In fact, we bring in data from more than 100,000 different types of sources. We bring in narrative data like news and social media or industry publications, financial reports. We bring in environmental sensors, think earthquake sensors or weather sensors. We bring in cell phone telemetry data. Where are cell phones congregating? How are they moving? You've probably seen a lot in the news recently about how cell phones are being used to track civilian movements related to the pandemic. Are people complying with stay at home? Are people crossing borders? So we bring all of that different kind of data in. And what you're looking at in this view, this is actually a dashboard and powered under the covers by Elastic, of course, that kind of shows some of the things that I as an analyst am interested in. So I'm looking at refugee events related to the Mediterranean. I'm looking at a set of natural disasters. I'm being notified every time new imagery is taken over parts of the world that I care about. I'm tracking what's happening with Saudi oil prices, particularly as it relates to events that are happening in the war in Yemen. You can see BBC monitoring. BBC is a partner of ours, and we pull in their data. They also use our system as part of their production of monitoring data as well. So it just kind of gives you a feel for the type of data we can be looking at. Again, here's more alerts as they come in. So you can see things like alerts generated by news or social media. You can see alerts generated by environmental sensors. In this case, the earthquake that hit Alaska about 1.5 years ago. You can see imagery alerts. When was a new picture taken over a place that I care about? In this particular story, one of the things we're tracking is the movement of ships and commerce around the world. And one of the things we've been watching is arms smuggling going into Libya. There's a big civil war there, so we're tracking where are military supplies going. And in this case, one of the combatants there captured a ship that was shipping weapons from Iran to the other side. And what we're seeing here in the center of the picture is that arms freighter being unloaded by those cranes. Those arms are likely to be used against the forces that actually were trying to buy and smuggle those in. And this is an example of a report that would be put together using all this different data. So you see satellite imagery, you see ship tracking data, you see narrative data coming from news, you see a reference information about the ships and about the port. So that can all be combined very quickly into a report that can go out to our customers. And those customers may be government customers. Those customers could be commercial entities who really care about what is their global risk posture, what kind of disruptions could they potentially see to their supply chains and their economics. Here's another example. And what we're looking at here is a series of satellite images. And what you're seeing shaded is basically the changes. So the red blobs are basically freighters, iron ore freighters that are moving in and out of the port. And the yellow and blue shading is the piles of ore that are being transshipped onto these freighters. And so we're watching what is the volumetric change over time to those particular piles. And this is called imagery-derived analytics. We use machine learning and AI, computer vision, to do this work. Elastic sits under the covers as kind of the master database for all of this different content that's flowing through the system. So here's an example of a dashboard. In this case, we're tracking what's happening at that particular iron ore port. You can see things like the vessel schedules of what ships are coming in, which ships are expected to leave, what ports did they come from, where are they likely going, who are the entities involved in terms of the ship owners, and what's the congestion that we're seeing? What is the throughput of that particular port, and how do we measure that and look for anomalies? Here's another example. And again, we're bringing this data in from a lot of different sources. Here we've gotten a seismic instrument warning of a large earthquake that happened in Ridgecrest, California last summer. And what you're seeing here is several things. One is, where is the epicenter? What is the potential damage map based on soil types? And then all the blue and green dots are facilities. These are critical infrastructure facilities or customer facilities, and we're basically tasking those for our satellites to go take pictures. So within seconds after an earthquake happens, our satellites are already being reprogrammed, retasked to go and get images of those facilities so we can do some immediate damage assessment to figure out whether those critical infrastructure facilities are still in play or not. So again, it's this idea of what kind of things can you monitor? We monitor activities, but we also monitor very specific sites and facilities. So think airfields, think ports, think critical infrastructure or energy facilities, oil refineries, offshore platforms, urban centers, sports venues, anything that is kind of fixed on the earth and has some change related to it is something that we can take pictures of and track. So here's some other examples. Here's an airfield in Iran that we're keeping an eye on. Here's a Russian airbase up above the Arctic Circle. You can see that the runway is actually still covered with snow at this point that we're taking this picture. Because we can do this monitoring, it's not just taking pictures, it's actually measuring what's going on at those facilities. So in this particular case, what you see is an airfield, and our computer vision algorithms have identified the different types of aircraft that are parked at this runway. You'll see light blue and red, dark blue, yellow. Each of those represents a different type of aircraft. And then we're bringing in other contextual sources of information, like the defense journals that are telling us that new planes are expected to be deployed here. Let's watch for them. And you can see some of the graphs in terms of timelines. What this allows us to do, if we're collecting at a high enough cadence, basically if we're taking enough pictures, we can then graph the number of aircraft over time and look for anomalies. Where did all the aircraft go? Did they deploy somewhere else? Are we seeing a surge of aircraft that we hadn't seen before? Is there an unusual level of activity? Or is this the normal, Monday through Friday, reservists on the weekends kind of pattern that we would expect from Russian doctrine? Here's a different example. We're tracking a nuclear reactor. It's under construction. So we're really watching as the construction progresses, what are the stages to get this nuclear reactor turned on? And in this case, it's a very large reactor in the United Arab Emirates. It's being built in conjunction with the South Koreans. And so we're basically tracking activity at the plant from space and combining that with data coming from other sources to get a contextual view of what's happening at this facility. Is it on schedule? Are they working overtime? Have there been problems with the construction? Do we think that they're complying with non-proliferation rules? And here's an example of the kind of report that we build based on those observations. So here an analyst has gone in and taken a time series of imagery that's taken at different points of time and looked for the activity. In this case, we're taking the pictures so frequently that even things like the position of the cranes will tell us whether they're active that day or not. So the way this works, what's kind of under the covers behind these capabilities? Well, basically what we've built is what we call a global intelligence platform. And that's an analytics platform heavily reliant on Elastic, hosted in Amazon and using a lot of different Amazon services, with an engine that's built based on machine learning, artificial intelligence, computer vision, and natural language processing as some of our key techniques. We bring in data from lots of different sources. So you'll see there the BlackSky constellation. We also bring in satellite data from other sources, imagery, synthetic aperture radar, radio frequency, multispectral data. We're bringing in data from third-party sensors like IoT, mobile, environmental sensors. And then again, we're bringing in all those different narrative sources, text-based sources, internet scraped-based sources to provide some context to what's going on. And that allows us to do things like detecting change or providing indications of warning of anomalies, being able to do very high revisit imagery to get a pattern of life. And by doing pattern of life, we can do predictive analytics. So let's talk a little bit about the architecture, and we'll start getting into how Elastic plays a role in this. This is very conceptual, but the idea is that we have a series of different types of processing pipelines depending on the type of data. So for example, our narrative pipeline is all about processing unstructured text data. So there's a lot of natural language processing in there to extract entities and actors and locations and organizations out of the text and try to nail down things like time and place where those activities happened. We have an imagery analytics pipeline that's very much about processing raster data and then using computer vision techniques to extract objects, to count objects, to look for change within the images. The instrumentation pipeline and the tracker pipelines are both about bringing in observations. Instrumentation pipeline is more about scientific observation. The tracker pipeline is about things that move. So think ships and trucks and containers and aircraft. That gets processed in that pipeline. These pipelines flow in and are stored in essentially a big data lake. And our data lake is based on Elastic. And from that, we generate what are called events. An event is some activity that is happening. That event may be based on a single source, or that event may be based on dozens and dozens of correlated sources that all relate to that one activity. So for example, if a ship leaves Libya full of refugees and floats out into the middle of the Mediterranean, that's an event. But we may hear about that from many different sources. We may hear about that through social media. We may hear about that through ship tracking. We may see it in our imagery, but it's all the same event. We enrich those events by pulling in information from other sources, and we correlate those events so we can try to make sense out of what is essentially millions of observations a day into a handful of categorized events around themes like conflict, crime, health outbreak, pandemics. We're dealing with that one a lot right now. Natural disasters, military activity, energy and critical infrastructure, economic alerts, and construction alerts as well. The information goes out through a series of alerts and notifications and dashboards, as well as APIs that allow us to plug in to other systems. And then the final thing on this chart I'll point out is where it says brokered virtual constellation. That's a fancy word for saying we can interact with satellites and other data sources, not just in terms of being a consumer, a streaming consumer, but actually tasking them, telling them what to do. So when something happens, we can tell our satellites, go take more pictures of that. We need to understand more about what's happening. So let's talk a little bit about Elastic and how that is a key component of this BlackSky platform. We use Elastic a lot for geospatial queries. So we've spent a lot of time tuning Elastic to make sure that our geospatial queries are as fast as possible. We're often searching tens of millions of polygons at a time, and we need that response time to come back in the time it takes a user to essentially pan and zoom across a map in a web browser. So that requires some very, very fast performance. So we spend a lot of time figuring out how to tune Elastic to make it optimized. We take advantage of a lot of the work that Elastic has done around geospatial queries. It's a very common topic of discussion with us and Elastic around how do we make those faster and faster. That's a really key element of our architecture. What you're seeing in this screenshot, this is basically saying, pull me back every satellite image that was taken in the last month over Southeast Asia. And each of the little rectangles that you see is a different picture. It's a different shot that was taken, and the different colors represent different satellites. So you're seeing here literally tens of thousands of results taken by dozens of different satellites. And those queries are Elastic powered. So as I pan and zoom and change my search parameters, that stuff needs to pop up instantly in my web browser. Here's another example. We have Elastic is not only kind of driving our data lake, our geospatial catalog, but then we're running analytics against that. And many of those analytics are based on Elastic queries. So you can see here, we're tracking movement of ships and movement of trains as they move iron ore in and out of Australia. You can see we're tracking trends related to congestion. We're even tracking trends related to the prices of commodity ore and how that's changing based on throughput changes at this particular port. The geospatial catalog is really the heart of how we're using Elastic. It consists of data coming from many different sources and many different vendors. And that's important because it means that the structure of the data coming from many different locations is not something that we try to prescribe into a strict taxonomy. Kind of like an old relational database. This is very much about NoSQL and using techniques like data lakes to be able to shove all the data into Elastic and then run our searches against it without it being an overwhelming database rationalization, normalization, third factor, type of exercise. Elastic has been ideal for us in that regard. It also means that we can add new types of data very, very quickly, because we essentially, I'll use the technical term, we shove the data into Elastic, and then we build our queries against that without having to worry about spending a lot of time really trying to figure out how do we do normalized relational databases like the good old days. There. In addition to having this giant geospatial catalog of data coming from all these different sources, we also build analytics on top of it. And part of what you're seeing in this view is I'm looking at a particular event, Turkey presses Syrian assault as thousands flee the fighting. You can see here, if you look at those large numbers, you can see it's a refugee event. It has an image worthiness score of 7. That means this is a good image to take satellite pictures of. Some events are not. A kidnapping, while very important, it's pretty hard to chase that with a satellite. But things like a Turkish military incursion into Syria, very high image worthiness score. You can see things like the number of data sources. 112 data sources are going into this particular event. And it's actually a super event built out of 17 lower level events across 12 different media sources. You also see the anomaly score of 8. That means it's pretty high. This is not something that happens every day. This is not a normal pattern of life. In fact, that anomaly score and that image worthiness score would result in an automatic collection by our satellites without even having a human in the loop. It would just see the score and go, I need to retask the satellites. I need to prioritize this area for satellite collection. And again, these analytics, the queries, and the underlying geospatial catalog is all based on Elastic. The other thing that we're doing, because we're telling the satellites what to do, we essentially have an e-commerce thread, an e-commerce process or workflow. And that's how do we process orders? Because every shot costs money. So it's not just a matter of making sure you have the shot. It's a actually fairly traditional e-commerce workflow where we have to track order status. We have to track order fulfillment. We have to make sure we invoice the customer correctly. We have to make sure that the task was done on time. There's customer support functions and ERP and CRM functions related to this. So part of what you're seeing here is that in addition to kind of Elastic as our core database or repository, we're also using other Elastic products like Kibana to really build business intelligence, or business activity monitoring dashboards and reports, so that management can kind of keep track of what are we doing and are we keeping our customers happy in terms of order tracking and reporting. We also do a ton of logging and monitoring. And in fact, this is a pretty big effort for our infrastructure, for our DevOps team, is spending time making sure that we have thoroughly instrumented our processes, and that logging and monitoring is being mined and feeding into our BI and business activity monitoring dashboards and anomaly reporting. So you see some examples here. We're running with utilities like FileBeat, MetricBeat, PacketBeat, a lot of Logstash, and we're also doing quite a bit of monitoring, including being wired directly into not only our DevOps processes, but our development team itself through things like Slack and PagerDuty. A lot of pulse monitoring or heartbeat monitoring going on as well. And with that, I'll stop and take some questions. I've also got a couple other of the BlackSky guys on, so if you have any specific questions about our implementation that I can't answer, I've got some reinforcements that can help me. So Faith, with that, I'll open it up for Q&A.
Awesome. So I don't see any question. Oh, here we go. All right. So how do you balance indexing throughput and search performance at the scale you operate at? Have you automated that process, or does that require ops intervention if any performance bottleneck alerts go off?
Yeah, so in general, it's fully automated. And as I showed in the one chart, we have different pipelines. And even within those pipelines, we tried to build it from a parallel processing perspective, multiple threads. And so we've instrumented from the perspective of watching for throughput spikes. Because of the way we've configured our auto scaling within Amazon, we will auto scale our ingesters up if we see a surge. The other thing that happens with a lot of those sources, some of them are streaming sources that come in 24/7. Some of them are very bursty, which means we might get one big update every 24 hours or every 8 hours. And so auto scaling in Amazon is one of the primary mechanisms we use to throttle up and throttle down all those different ingest threads. The other advantage to doing it that way is from a cost control perspective. It means that we don't have to have a lot of idle processing. It means our operational cost curve is very, very close to, to our performance curve as we scale up and down. The other thing we've done is we've been running this for a while now, at least for a few years. And so we've been able to kind of tune it for what we expect to be normal performance, including when are the typical spikes, is the auto scaling working correctly, how much lead time do we need on auto scaling. But predominantly the way we're doing it is we're running multiple instances of our ingest. We have multiple instances of Elastic, and we use Amazon auto scaling as a primary mechanism. And I don't know if Derek or Kevin can come in. I think they're attending as participants, but if they have anything to add.
Yeah, I can give them speaking power. You said Derek and who was the other person?
Kevin Riolas.
All right.
And he's pinging me saying he wants to answer.
Okay.
So he'll correct me with what I said wrong.
I think he can talk now.
All right, can you hear me?
Yep.
Hey, there's Kevin. Hi, Kevin.
So, how you doing?
So Kevin is out of Tampa, Florida, and he's he runs the DevOps infrastructure team here at BlackSky.
So to get a little bit deeper into the question about how do we deal with the indexing and the search performance, like Scott said, we do tend to auto scale pretty quickly. Beyond that, we use watchers, and we keep a very close eye on a couple of key parameters, and we'll fire off immediate PagerDuty alerts. If we see garbage collection getting a little bit out of hand, that's always a good indicator that you're killing memory. And we specifically watch for the young collections. Old collections don't tend to hit the CPU that hard, but when we start getting too many young collections, meaning our ingestion's running, indexes running, we've overloaded what we have up we'll normally trigger an alarm at about 60%, since 75% is the magic number. And we'll go in and manually throw a couple more nodes at it. And like Scott said, we are very bursty. So if we have a huge amount of data come in, generally we try and do our burst ingestions on non-peak times, unless there's events going on in the world. So on those special occasions, instead of trying to automate that edge, we just send out an alert, wake ourselves up, and throw a couple more boxes at it for a short period of time.
And Kevin, part of that question was, does that require ops intervention if any performance bottleneck alerts go off? So
Yeah,
how often do you guys actually have to intervene versus auto scaling and other tuning just kind of picks up the load at 4 in the morning?
Well, for that specific case, then we do. So if we see, for normal ebb and flow and growth and shrink, we auto scale and that works fine. But when we start seeing a trend where garbage collection events aren't keeping up, we had this before with analytics cluster when we had a large ingestion happen while people were querying it. So we split it up that way. We haven't found the need to create separate ingestion nodes and separate query nodes and isolate like you can yet. Again, because it's pretty quick for us to jump in, and then it's automated for us to increase the cluster. But yes, ops does get involved for that special edge case, mainly because the scale down for that, because it's so batch related, it's very difficult to figure out how and when to scale down from an anomalous spike, right? You really don't know that well. So we just over provision for a short period of time. As the curve drops, then we'll come back down. And those occur, the cases that occur outside of our need, outside of our automated process, are one to three a year. So again, there's so much edge case that we handle those pieces that way. Everything else is automated.
Thanks, Kevin. And if you can stay on the line, there's several more questions coming in that I'm going to ask for your help with.
All right, I'm here.
All right.
Awesome. So the next one is, what does your overall architecture look like? How many nodes have spun up, etc.?
So what we do is we have multiple clusters. We have the classic elk stack, and for our logging, we only tend to keep 2 weeks of data. So for the elk stack, I run 5 data nodes on i3, 2 extra larges. I use the i3 family because I can use ephemeral storage. It's a lot faster. I have 3 Logstash nodes. I have 3 Kibana nodes. Both of those can auto scale, and they do it. So, and they're both behind load balancers. I did not put the cluster behind a load balancer because of the chance of IPs changing. I didn't want that to get in the way. And then we run a curator node. This is for the elk, and curator manages some of the indices like the dot monitoring that aren't auto, that you can't manage easily with ILM. For our production clusters, our other 2, those go anywhere from 5 to as high as 20 nodes, depending on the need for data. We're on 7. We also have 3 master nodes per cluster. That's new as the 7X. So on the production clusters, we have the data nodes. We have Kibana because we do visualizations and dashboards and alerting based on what we see. And then the master nodes, and everybody has curator. We also use curator to do things like kickoff, scheduled snapshots, just the general maintenance stuff that we wanted to keep within the cluster family. So that's our general setup.
Awesome. Another question relating to our kind of your setup is, how often have you had to adapt your shards, and what sort of magnitude operation has that been?
That is an excellent question. So
you knew we were going to get a shard question.
So when we went from 5 to, we've been on since 1.x. So we've been running, and the data for the operational clusters continues to accumulate. We've got heck, actually decades, because of the back ingest. As time changed, rules changed, and the real goal of getting about 50 gig per shard to find that magic balance of how much heap you're using versus how long it takes to index and everything else, and then how many, do you have one replica, two replica, etc. We did a really, really hard look when we went from 5 to 6. So this, I guess, is about a year ago. When we converted, when we did our big change from 5.x to 6.x, we also did on one of our operational, we have 2 families of operational clusters, and then we have multiple accounts. So it's not as easy as one account. We have several customers, so we have this entire setup repeated multiple times with different data sets, but the same core data set in the case of our analytics. And we took a really hard look at how everything was laid out. And as we were starting to get in all this data, one of those anomalies I talked about actually caused a garbage collection storm, and we had a real issue. And it was because we had our shards were far too small. We had too many. So when we did it, it wasn't difficult. It was time consuming because we really did have to do a full reindex. The way I did it to not bring us down was I created a new cluster, an interim cluster. I restored my latest snapshot into that cluster. That takes a few hours. Once that was done, I made the cluster large enough so I could do a local reindexing so it'd be faster. So but I did have to completely reindex the data to get into the new shard sizes. Right, new stuff that ingests can meet the new requirements, and we do everything with ILMs now. So everything's auto rollover, dates, time, sizes. But when we first did this, I needed to stay operational, so I created the intermediate cluster. I then reindexed everything into a new set of indices on that cluster. So when I did my restore, you can stick a prefix name on there. So I did that for everything. Reindexed into the proper name, so now everything was sharded as I wanted. Everything had the right number of replicas. Everything was laid out as I wanted. I deleted the indices that I restored, so now I had old and new. Then I just did a remote reindex to catch up the new cluster with the old cluster, and then I switched and pointed to the new one. So downtime, we were able to keep downtime to a real minimum for such a large data operation, but the period of time from the restore to the reindex to the then remote reindex, it was several days. It was, it's something you have to keep your eyes on, and it takes a while, but it is a scriptable process, and it's something you can follow and get done pretty cleanly.
Awesome. So the next question is, have you considered using hosted Elasticsearch either by Amazon or Elastic, and what drove your decision to not use them?
So for the Amazon one, it's mostly feature compliant, but it's not completely feature compliant. And we do have some use cases where we have to consider running outside of Amazon. So there's a bit of hesitancy to put our core data environment specifically into another vendor when we might not be able to run everything there. It keeps it a lot easier if we can manage it. We have considered switching to the cloud solution provided by Elastic, but the same exact reason comes up. There are a couple of situations where we may have to put our data on premise, and on premise without easy internet connection. So the best solution for us right now remains to be running our own instances and our own deployment of the full Elastic stack.
The other thing I would add on there too, in terms of the difference between the Amazon hosted or Elastic hosted, was that we had some concerns about the differences in the versions between the two of those. Right. Because we have been working closely with Elastic on the tuning around geospatial queries, that meant that we really needed to be running the latest, greatest version of Elastic. And that may not be as big of an issue now, but when we were making some of these architectural decisions, essentially the generation version numbers between what Amazon offered and what Elastic offered the delta was too big. So that was part of the decision process as well.
Right.
Awesome. All right, next question. Are you using another platform in front of your Elastic platform to reduce back pressure, such as Kafka or another messaging platform?
Nope. No, we found that Elastic keeps up pretty well. For our biggest, frankly, probably everybody's biggest, depending on how much you log, our biggest data influx is logging. And we do use Logstash to bring in all the CloudWatch logs, and we do everything, including VPC, flow logs, full ELB logs. And we everything that comes, every piece of data we can pump into logging, we pump into logging, and it keeps up without a problem. We haven't seen it. The only thing I do is I do have load balancer in front of Kibana and in front of Logstash. Actually, no. Mainly Kibana, just because it's easier. That's the only reason I did it. I could have used Service Discovery to do the same thing, and for on-premise, that's exactly what I would do. But other than that, no. I find it a lot better actually to let Elastic manage the flow as much as possible, because it does a good job doing it.
The other thing I would add there too is the kind of volumes we're talking about. I mean, even if it's millions of observations per day, that's still pretty small numbers in terms of streaming data flows. So we're not testing the system the way a lot of other companies out there are. So we are not an edge case when it comes to throughput volumes.
Awesome. Okay, next question. Are you using Compute Engine or Dockerized Kubernetes version of Elastic for your clusters, and why?
No, we are not. Again, the main reason is for storage speed. So we're running on instances. I was about to say bare metal, but so virtualized at this point. We're running on instances. The reason we're running on instances is twofold. One, and the primary reason, is that I can use ephemeral data store. So when it comes to your clusters, the slower your disk, the slower everything else goes. So, as you optimize, you try and clean out everything that's slowing you down. And by getting to ephemeral storage on those instances, it allowed me to really speed everything up. With containers, I would have been stuck with mounting, whether it be EFS or just using block store that's allocated to the container. There'd be speed issues for me. Other people have set it up and fine, and we did try it. We tried using containerized and running it that way. It just didn't give us enough kick. So those are the reasons.
Got it. Are you guys using Logstash for all your ingesting, or Python or another method?
All of the above. So we use Logstash literally for all of our logs, for everything that comes from the Amazon environment. We pump through Logstash. We just recently stopped, as the beats have been improved over time, we just stopped pushing the beats through and have started to convert, once Elastic released their common schema, and have started to convert everything else we're bringing in to make sure it just matches the common schema. For our production ingestion, we do that directly from Python. So because we have our ETL is fairly customized. And again, remember, we wrote all this back in 1.x and have grown from that. So we've moved all that there. We are having these are extremely high level and background talks now about possibly moving some of our news processing to Logstash. But for us, that'd be a pretty heavy lift at this point. So unfortunately, some of what we do is anchored in what we did when we started at 1.x.
Yeah, the other thing I would add there, if you look at the chart that I still have up, each of those pipelines is a series of pre-processors that have to massage that data. As I mentioned during the briefing, in general, it's a data lake strategy, shove it in and sort it out. But each one of those data types, there's very different characteristics to it. The tracker pipeline where we're talking about movers, right? Those are a bunch of data points that have to be assembled into tracks. If we're looking at imagery analytics, we're invoking computer vision models on that inbound imagery. So it's a lot more complicated than just processing, log entries, for example. Each one of those pipelines is a custom ingester designed for that type of data, the phenomenology related with that type of data.
Okay, got it. With using ephemeral storage, what is the ramp up time when you need to bring a new node online?
Extremely fast. So when we try, and I say that based on having done this with old EBS when you have to do it. So we do two things with the instances. One, we pre-build custom AMIs. Right? We actually use Packer. So we use Packer. We pre-build it, and what we do is we bake on CloudInit scripts. So instead of trying to use just the user data, we actually use the CloudInit functionality, and we're trying to streamline that part to customize that node so it auto joins the cluster and everything else. One of the things we have to do is we create a virtual disk out of the ephemeral store, just in case we need to add more disk space later. We can throw it on there in case of an emergency. So we use Logical Volume Manager. All of that stuff runs really fast. So we're probably from the time an instance gets notified to start up to it being a member of the cluster is 30 seconds, 35 seconds, which for what we need to do is extremely fast. So.
Awesome. Follow-up question to that. And is there a tipping point whereby you would struggle to populate ephemeral storage while servicing incoming requests?
I don't think so. Of course, and the reason I say that is we tend to keep, we alarm at 50% storage. So, and it's more of a function of the sizing of the instances and the storage associated with them in Amazon, because what we find is our larger instance requirements come because we need to have enough memory to have enough heap space, right? As we grow nodes and shards, that the amount of space has to grow, and our memory requirement is usually greater than our disk requirement. So we're rarely over 40% as we've grown, and then I fire an alarm at 50%. So we usually get a good 3 month or depending on how fast, and so at least a 1 month notification that we may be having a problem.
Hey, Kevin,
go ahead.
I was just going to say a follow-up question on that. I talked about during the brief how sometimes the data is bursty, but that's still kind of the activity monitoring. But the other thing that we do is we'll actually get batch mode ingest as well. Like one of the things we just did recently is we ingested a ton of Hawkeye 360 radio frequency data, and we went back like 3 to 6 months and just shoved it all in. Can you talk a little bit about, do we just do that through the normal process and let the autoscale handle it? Or does that require any special handling around the way we deal with ephemeral storage or any other aspect of the ingesters?
So specifically for that, and actually it was more, not this one, but we did a full year reload in a test environment. So I could have let the autoscale handle it, and what would have happened with that. So in that case, the speed, to answer both questions at once, it wouldn't have alarmed quickly enough for the 50% alarm, but I would have caught it at the 70%, oh my God, disk space alarm that we have.
Yeah.
And it still would have been enough time for everything to handle itself. However, if I know that something's coming, like a large batch ingest, where I know things are going to change, it's easy for us to just go and grow the cluster beforehand. And frankly, it's a little bit easier that way, because like in this case, I opened up 100, I let our ingest containers that were running in Docker, I let them scale out to 100 containers at once. So we were really slamming the cluster pretty hard.
Yeah.
So I knew that was going to happen, so I pre-grew it. But no, generally, and when in the last 4 years, I can think of one time that the disk grew quicker than everything, the alerting and everything else we could handle. And of course, once it gets too large, then the clusters or the indices are marked read only. And recently they changed that so they'll autocorrect, but we did have one occasion where that happened, where we grew so fast that all of our indices went to read only, and that was a bit of a scramble. And that was actually the birth of the 50% warning as well. So we can automate it and handle that. And we haven't seen anything bad since then.
Awesome. So the next question is, i3 nodes with local ephemeral storage is blazing fast, but that means it is critical to do regular snapshots to S3, right? If a sudden Amazon screw up happens and they inadvertently terminate a few of your instances at the same time and the ephemeral storage vaporizes, then you could lose data.
Correct. So we run nightly snapshots, and what we do is, they build up on themselves. So instead we don't run a full snap, we allow incrementals, and then we actually rotate when we create the we do it to S3. When we create the S3 path, I create that with a month boundary. That way I'm guaranteed to have one full snapshot per month. I always maintain 3 months, the last month, the current month, and then when I roll to a new month, I won't delete the old one until I've started the third month. We do those nightly, and then we actually have an audit account where we synchronize all data backups from everything we do, and we keep those forever. So we have every snapshot we've done for several years in our audit account, and we use tiered storage for that. I did have an occasion where it wasn't that Amazon screwed up. It was there was actually a hiccup in a deployment that brought down some nodes, and we had to do a restore. Fortunately for us, we have multiple accounts, and like I said, in a lot of cases the data is similar enough, so I was able to point, and it took a few hours to restore it, but the outage wasn't the end of the world. Even for our central catalog, because we run development, integration, test, and operational environments, and we try and keep parity in our data between those. If I had to, I could point to a different account completely for a short period of time while I recovered. But we do run nightly snapshots.
Got it. Okay, the next question is, have you found the limited SQL capability of Elasticsearch/Kibana to be a challenge for your analysts who traditionally are more used to relational joins, etc.? Or have you found a way out of it with any third-party integrations?
So
I
can you go ahead first, Scott, and then I'll...
Yeah, so the first one is, even though it's an analytic platform, what it's doing is it's producing canned alerts and notifications and reporting. So there's not really the idea of an analyst going in and kind of free-forming their own queries. They do have a way to construct what we call channels, which is how they identify topics of interest, and they can combine things like keyword searches and do some fairly basic Boolean operations that we then convert into Elastic queries and stuff under the covers. Hasn't really been a big limitation. But again, the use case is not an analyst kind of going in and generating their own complex queries. Kevin, do you want to follow up on anything we're doing there in terms of how we're doing complex queries?
Yeah, so it's actually funny, and I do understand the question coming from, obviously being an older guy, relational database. Our developers and our data scientists don't like SQL. So using Lucene, using NoSQL type query languages actually seems more natural for them. So even when they jump into Kibana, and whether they use KQL or they use Lucene, they're very comfortable with both. It actually took a bit more work to get everybody refocused. We do have a relational database for some other stuff that's highly relational. And it took a lot more work to get them to use SQL queries again than it did for them to work in this environment.
Yeah, and there's another question coming up in the queue here that's going to talk about what else do we use besides Elastic. So I'll follow up with that question and answer more about this. Where do we go relational and where do we go pure NoSQL?
All right.
Okay, so is Elasticsearch being used for all of your persistence layer? If not, why not?
Yeah, so the answer there is most of our persistent layer, but we do have some other databases. We've got a bunch of lookup tables in Dynamo, for example. We actually have a GeoServer instance running on PostGIS. And so there's some relational queries that kind of happen there. Most of the tough queries that we do, it's not so much that there's a ton of complex, quote unquote joins. It's because we're very, very focused on geospatial and we're very, very focused on time and combining those two together. So most of the complexity in our queries is about how do we take data from disparate sources and match it up, in the same location, right? So it's bounding box queries and polygon queries, and determining the stack of data that lives within those polygons. So we do have a couple other persistence databases out there besides Elastic, but Elastic is definitely the lion's share. And Kevin, I don't know if you want to add anything there.
Actually, well, so the other part of it is we use Mongo for our internal really configuration management and user settings, things like that. We kept those separate, mainly from a lock and key perspective, right? So even though we could do row level security or index level security, document level, sorry, or index level security in Elastic, when we created the two things, those are functions that are more toward the operation of the system rather than the use of the system. And like Scott said, since we're so geared for speed, our indices are highly tuned to very specific data to allow it to be a lot faster in Elastic.
Awesome. So I think that was our last question. Thank you, Scott, for the presentation. Thank you, Kevin, for chiming in with some answers here during the Q&A. But this was a really awesome, really cool to see. And thanks again for coming on.